I'm Matt Godbolt.
And I'm Ben Rady.
And this is Two's Complement, a programming podcast. Hi, Ben.
Hey, Matt.
How are things?
Not too bad.
Cool. Well, unusually for us, we have a topic before we started today, because yesterday you and I got coffee, and I got excited, and then we both were like, I wish we'd recorded this. So we're going to try and have that same conversation again with the same level of excitement and enthusiasm, which, you know, is a bit of a struggle for us both. We're not very passionate about what we do.
We're not normally enthusiastic people.
No. So we'll have to try that.
Every moment of this podcast has been pure pain. I'm just going to admit that up until I've been keeping it hidden up until this very moment. Until this
second, and now the public revealed to the public. Yeah.
Yes.
I mean, we've already told everyone that this is like extremely low effort podcast. We go out of our way to make it as simple as possible for ourselves, even though, you know, I still like the fact that we do transcripts and that we do edit them a little bit. I try and make my dog not make a noise in the background.
Good luck.
I know. He's just started moving. I can hear him. We'll see how this goes. But today, I wanted to talk to you about some cool programming stuff that I've actually been doing. You know, after our last conversation where we said, hey, it's kind of cool to be a programmer and not be a people manager, that has come to pass in the last few days. So, let me phrase it as a puzzle to you.
Okay.
So these are the set of constraints that you have. You're writing a piece of code where you have many threads, possibly many processes. There are some important critical pieces of information that you need to share between these various programs. And it's imperative that at no point do you prevent the producer of this information from being stopped or blocked by anything.
Okay. Yeah.
You only need the most recent output. So imagine it is, let's say it's the current S&P 500, right? Whatever the S&P 500 is, something's happening, you're measuring it, and then you're writing the value to somewhere that many readers are then going to read from. But obviously, this information is big enough that you can't just write it in the hope that everyone sees the output.
Right.
Exactly as you wrote it in.
It's many bytes.
It's many bytes. Right. Exactly.
Yeah.
So, how do you design a system where you can share small, but not trivially small, pieces of information between threads where you never block the writer? The readers need a fast access to it, but you don't mind if they have to, if they have to do a bit of extra work. So there are actually many solutions to this. But what comes to mind?
Well, I mean, you haven't mentioned anything about the latency constraints.
Correct. Yeah.
So given the fact that there are currently no latency constraints, I can think of many solutions.
Well, actually, go on then. So let's think of a latency constraint where we don't block the writer. At no point do we block the writer. So think of, what can we do?
So going back to one of our previous episodes on building boring things, files, you could use a fan out queue. You could use something that if you don't care about sort of like if a receiver of this information is expected to handle a situation in which it's falling behind by just losing information.
Right, which is absolutely the case in this. We only care about the most recent for the receiver.
You could use some sort of network broadcast to just broadcast it out. And it's like, if you're listening and you get this, that's cool. And if you don't,
that is cool.
You don't. Which has some of the same properties as a fan out queue, but isn't exactly the same thing. Those are probably the top three. Again, modulo no latency constraints. That's where I would probably start as one of those three.
If you drop RAM constraints and things like that, you could just have an append only queue, and then the readers only look at the most recently written.
Well, that's what I was saying. My first one was files.
Yeah,
right? Like, here's a file. Start. The messages are fixed length, so start at byte 0 and read, and then when you hit the end of file, try again.
Right. And then if you
just keep
read
going.
if you want to read the latest, you don't care about the intermediates, which is perhaps something I didn't state very well. Then you seek to the end of the file. And if it's not a multiple of the object size, then you know that you've kind of caught the writer while it's still writing. So you mod it, something like that. And that gives you...
That'd be really dumb and would work.
Exactly. Yeah. And all of those things I think you could make work. But yeah, then to get round back to the obvious part here is that like we don't have infinite RAM. Files are probably not a good choice. And we're looking for the lowest possible latency. What is the fastest possible way that you could share this information? Again, the writer probably is going to be updating this very commonly. It's, some derived financial thing. And then the readers from time to time need to be able to look at it and kind of say, is this... What is the current price? Maybe it's even like a web, a web view of like, what is the current S&P 500? And you're like, okay, I don't care how long it takes my web service to read the current value out. It's just, but it is a consistent value,
right?
It's not like half of.
You don't get half the bytes.
That's
like,
right.
Wow, the market looks cheap today.
Yeah, that's a very bad mistake that you make usually only once in a career.
Yeah.
So yeah, one of the solutions to this problem is to use a relatively unusual and fun construct called a sequence lock. It's used in a bunch of places in the Linux kernel, so it's kind of well-worn and well trusted, but it has some interesting characteristics. So let me explain to you what a sequence lock is, and then we can talk about why it's kind of difficult to get this right, and why I've spent a week trying to write one and not sure whether or not I have actually got it right or not. So the trick is this. If you are a writer, well, first of all, the piece of information is in a shared piece of memory, and it's the same piece of memory for that. Like, we're not using it like a queue. It's just one place to look for a particular value. So like, this is the S&P 500. It lives at this address in some piece of shared memory.
Okay. So the readers and the writers in this context have this shared memory. So they both have access to this memory, which means they're at least running on the same machine.
Correct. Yes, that is right.
They may not necessarily be in the same process, but they're running on the same physical computer. Or
that is correct. For this, yes.
Yes.
Same, virtual computer or whatever.
Uh-huh.
I mean, modulo, there are like, tricks to do RDMA and things like that across networks and stuff. But no, what we're talking about here really genuinely is a same computer, shared RAM chips somewhere in the system, right? And it's the same address. So, and as well as storing the piece of information that we want to protect, which has, as I say, is like 8, 16, well, if it was 8 bytes, we probably wouldn't worry about this. If it's 16, 32-ish, that kind of size of bytes, we also store a sequence number. Every time the writer goes to write, it increments the sequence number, it updates the data inside the block that's being protected, and then it increments the sequence number again. We'll get to why that's important. Lots of anyone who's listening who knows roughly what I'm talking about here is like already seen all the problems with the things that we've just talked about. But let's talk about what the reader does. The reader reads the sequence number. If it's odd, the reader knows that the writer is in the process of updating it. So the reader says, I can't look.
Right.
And it just waits a bit and tries again. So what we've got is very optimistic kind of attempt here. If it's even, we take a copy of the protected data. But that doesn't mean to say that it wasn't, while we were copying it, being updated by the writer.
Right.
So we've just read a bunch of data. We can't look at that data yet. What we're going to do is we're going to look at the sequence lock again, and only if the sequence number matches the first sequence number, when we read it, then we know that we got a good copy of the data that was being shared, and now we can look at it. It's safe to look at it. We know that the writer wasn't in the process of updating it, nor did the writer get and do an entire update while we were taking a copy of the information. Obviously, if the sequence number changes, we have to retry.
Right. So what happens if you have the slowest reader in the world? It's like a dude with an abacus.
Yeah.
And every single time you go to read the sequence number a second time, it's different.
Then you are in trouble, right? You're
just never getting this data. You're not fast enough. You need to be faster.
That is correct. Yes. So like in terms of testing, in the machine that I've got, I can get it to the state where if I have a writer that is fast enough that literally goes back to back doing modifications, then it is possible to completely starve out the reader.
Mm-hmm.
I say completely starve out. Every few microseconds, the reader was able to sneak in, but this is with a very fast reader, right? And on purpose, what we're talking about is a tiny data structure where you're saying that these are bytes that I'm going to like mem copy out of shared memory, so that like you're kind of hoping that like even if you're going to do something slow with it, you're going to do something slow with the copy that you got, the good copy that you got of the data.
Yeah.
And so it shouldn't matter too much. But it is possible. That is absolutely a trade-off you're making here. The writer can starve out the readers, but computers are super fast, and provided your writer isn't doing something pathological like sitting in a tight loop doing an update, even the loop overhead is enough to give the reader a decent chance of sneaking in from time to time, at least on a computer timescale. But it's absolutely possible, yeah. And if you care about these things, you probably need to make your API not retry or have a maximum number of retries and sort of fail for the reader and say like, hey, this didn't, I tried 1,000 times, it didn't happen. And then the reader could make a choice about it. So it's an interesting thing here. So again, the writer never has to block. The writer is able to just write unconditionally. So, for example, if the writer is processing a stream, a torrent of incoming UDP market data, as we do in our world, then it's imperative that you never block, because if you block for any length of time, you might miss some information on the network, and then you have to go through an expensive recovery process. So it has a great property for the writer. And for the reader, it has a bit of a tax. It's not free to do this check, but if the ratio of times the reader and writer are both looking at the same thing at the same time is effectively de minimis, which hopefully it would be, then essentially it's free on both sides. It's a cool data structure. It's used. My understanding is it's used in the Linux kernel to protect some of the data around the system time. So the kernel has some configuration information about, how fast the clock's running and all that kind of good stuff. It's bigger than it can atomically switch out, which is things that CPUs can do. And it's mapped into every process so that when you do get time of day, you don't actually have to do a system call. You can just read these numbers out directly of a piece of memory that's read-only in your process.
Yeah.
But the kernel can update it when, NTP is fiddling with the times, or, when there's overflows in some of the counters, the hardware counters that you need to use to actually work out what the current time is. But for the most part, the kernel doesn't touch that information. But if it does, it needs to do it in a way that's safe for all the processes to read from, and they don't mind doing a retry. So that I may be butchering the memory of exactly where that's used, but it's something like that. It's a cool thing to do. So
this reminds me. There's a Sylvester Stallone movie. I don't remember if it's Judge
Whoa,
Dredd.
I was not expecting it to go this way.
Yeah, it might be. I think it's Judge Dredd. It might be Demolition Man. I don't remember which.
I've only seen one of those. So
I think it's Judge Dredd. But there's a robot walking around selling food, and it's recycled food. And there's this thing that's playing. It's like, recycled food is good for the environment and okay for you. And so this data structure to me sounds like this data structure is good for the writers and okay for the readers.
That's basically it. Again, though, it does depend on the duty cycle of the writers and readers. And so even at the scale that we run at in finance, there are many microseconds in between packet updates, many single-digit microseconds in time packet updates, which is more than enough for even the most slow reader to get in and get a chance. Right. But even if they're delayed for a microsecond or so, so it's usually a win-win situation. And so it's fun, it's fascinating, it's interesting. But the real trick comes from the fact that everything that both the compiler and the CPU want to do on your behalf to optimize your code is at loggerheads with this very strict ordering of events. So like as I described to you, you absolutely the writer absolutely has to bump the sequence number first. Then it needs to change all of the data that it's doing, and it's got a certain amount of time to rummage around changing the data. Again, it's blocking the reader all the time it's doing this.
And the sequence number is odd while this is happening, which is a signal to the reader that it shouldn't be reading, right?
That's correct, yes. Yep. And this only allows for a single writer. There are extensions that relatively trivially let you have multiple writers for what it's worth. And then at the end, once you finish rummaging around and modifying and mutating your data, you need to bump it again to both make it even again to signify that it's okay to start reading it, and to be one higher than, or two higher than when you started, so that anybody who got a copy in between you modifying it also notices and knows to retry.
Right.
But those absolutely have to happen in that order. And if anyone's ever, for folks who are used to like regular programming languages, like, Python, the like, it's like, you write a sequence of statements, they absolutely do happen in that order, right? There's not anything particularly exciting. If I said A equals 1, B equals 2, A equals 3, at no point could you pause the CPU and look and observe that A was 3 and B was 2 or whatever. There's not like, sorry, that's a really bad example, and it needs a picture for me to even get it right in my head. But
yeah,
there's nothing funky going on there. It just does things one after another. But for an optimizing compiler, it's very convenient to be able to play fast and loose with all of the operations that you're doing, right? If you can pull forward something that's expensive that you're going to do later on, then you can start like a big divide or a multiply or whatever, while you're doing some other setup work. And then when you go to look for the result of the divide, it's ready for you. Hooray. Compilers want to do this all the time. So they want to be able to move the instructions around. And you need to be able to tell the compiler, no, you can't move these otherwise unnecessary looking memory operations.
Right. Is there anything that you can use to indicate that you're writing into memory that is potentially shared with another process, so that the compiler knows it's like, I'm doing this for the side effects on purpose in a way?
There is, there are. So specifically in terms of C++, which is where I'm strongest in this regard, a way to model this is to use the volatile keyword. That is not a good way, but it is a way. So volatile is on the path to being deprecated because nobody can really describe what it's for or how. But what it essentially says is, don't make any assumptions about this memory location. Okay. And when you're writing a device driver, or if you're writing some very low level stuff, then having a pointer that is a volatile pointer to something that's like mapped to, I don't know, a temperature sensor. So that when you read from it, you're reading the temperature. It's not real memory. It's just a thing that's a great candidate for something to be volatile. It says like, hey, this can change outside. Every time I say to read or write to this, you can't optimize about it. There's nothing you can do. Just do it.
Yeah.
So that is a way to do it. But most compilers will see the word keyword volatile and then start slowly backing away from your code.
They homer into the bushes.
They homer into well, certainly the optimizer does. Yeah. The optimizer says, oh, there's a volatile here. So as not to anger the gods of volatility, we're gonna not do anything here, right? So in your very critical code, you might arguments obviously exist for like, don't use volatile for this for other reasons, which we'll get to in a second. But specifically for shared memory, where another process outside of the program you're compiling could be changing it, there's an argument that says volatile is the right way to model it. So the short answer is, for shared memory like this, there isn't really a good way for C++ to say, hey, this bit of RAM outside of this program's remit will change under your feet. So the best we can do is we model it with atomics. And atomics have a whole bunch of things that come with them, right? One of the things is atomicity at the hardware level. Like if I read and write to an atomic variable, then it either happened or it didn't happen. You'll never see half of it written. Like if you've got an 8-byte sequence number or a 4-byte sequence number, there's no world in which I write that and somehow only the first 2 bytes of that 4-byte value have been written. That's what at the basic level an atomic operation is. And the compiler and will collaborate and generate the correct CPU sequences, or it will make it an error that this can't happen. Like, hey, you've got a 128 byte structure that we can't do this.
Yeah, you can't guarantee that. So
now that being said, actually, what it will do is it will actually use a spin lock to do bigger things. So there's a way of saying, please, you can assert statically at compile time that like, hey, can I do this without some kind of other lock being taken out? Because obviously the whole point of this is not to have a lock, so it would be really tragic to have something. But all modern CPUs will let you write 4 bytes and probably 8 bytes, and with some like very big caveat and footnote, 16 bytes using some tricks. But you can do those atomically, provided they're aligned, provided they're inside a cache line and they don't straddle 2 cache lines, all these kind of things. But like, we can assume that we can do that, but it's only a small amount that we can do that. But another thing that with the C++ memory model is that the atomics also model the fact that this could be being written or read from other threads. Now, obviously, if we talk about multiple processes, that's kind of a stretch to call it a thread.
Right.
But it's the kind of the best we've got right now. If you wanted to share between processes, it's certainly the thing that I've gone with here. Now, atomics are funny because reading and writing to an atomic doesn't necessarily, or sorry, reading or writing atomically to memory doesn't necessarily follow that the compiler isn't going to reorder things. It just means that you're literally writing to this memory location. So back in my atomically, in the example of the A equals 1, B equals 2, A equals 3 thing, you could make those all atomic. And I'm saying this is not C++ atomic. I mean atomic in terms of like the CPU can read and write these memory locations, and it either happens or it doesn't happen. And without telling the compiler, but you couldn't like elide the fact that A equals 1 ever happened. You can't throw the A equals away because you're about to overwrite it with a 3 later on.
Right.
That's a separable thing. But in C++, they're sort of bound together. And so when you say something's atomic, you're also saying something about the operations that can happen with the memory system, where the memory system encompasses both the compiler's ability to move things around and, more critically, the CPU's ability, which we'll talk about in a sec. So in the example of setting A to 1, setting B to 2, and then setting A to 3, if they were all atomic, the compiler wouldn't throw away the A equals 1 at the top.
Right.
Because it's like, no, this had some semantic meaning to something I can't see.
Right. Yeah.
At least by default, it won't do that. The default in C++ is to use an incredibly expensive, sequentially consistent view for atomic operations, which means that the atomic operations and the code around them happens in the one true order for even if you have multiple threads doing it, which is expensive potentially on some hardware that makes that an expensive operation to serialize. You could potentially imagine that, like, in order to make sure that everybody sees A equals 1 before anyone sees B equals 2, you have to kind of like add in instructions or like some other sort of ex machina way of saying all threads need to make sure that they're good. The caches are all consistent across all the threads. And now I can write to B. And then we go again, hey, has everyone got the B equals 2 if you care about it? And so on. And that can be a very expensive operation. And so there are these different ways of acting with atomics where you can give sort of a secondary semantic meaning that's less strict than this sequentially consistent view. Like, for example, you can say this is an acquire. So when you read, when you store a number in, you could say this is an acquire operation. I am acquiring a lock is the way I like to think about it. And then when you finish with it, you release it. And again, it's not like this has any meaning. We're not actually acquiring any locks or anything like this, but it has the semantics of a release operation and an acquire operation. And what do I mean by that? Well, if you're taking out a lock, it's a pretty big hint that anything after that is under the purview of that lock.
Right.
So if you've got 10 lines of code and line 5 takes out a lock, line 6, 7, 8, and 9 can't be shuffled above the lock because otherwise you're doing some things that you were trying to protect outside of the locked area.
Yep.
And then similarly, the release says nothing above the release can come south of the release operation itself. Because again, you want to protect things that are bounded by an acquire and a release sort of pair.
Yeah.
There are some other aspects to this to do with different CPUs and different threads and things that are much more subtle in this respect. But that is sort of the gist of it. And then you can also have like a relaxed operation, which says, I need it to be an atomic operation, but I don't really make any guarantees about which CPUs might see which values, as long as they're still atomic. That's more like the traditional original atomic that we were talking about, where it's just make sure this happens atomically at a hardware level, but imposes no other restrictions on the order of things. So it's easy to think about it from where I'm sitting in terms of acquire and release. And so you could imagine that in our case of our writer here, we write the incremented version, the value, with an acquire. We do all of our rummaging around, and then we write the secondary plus the second increment with a release. And it kind of tells me, my processor, that like everything I did between the adding 1 and adding 2 to the original number, the first increment and the second increment, is, for all intents and purposes, a lock.
Yeah. Yeah.
And that makes a lot of sense, right?
Yeah.
Unfortunately, C++ has some awkward, very specific to C++ things that make that not true, but that's fine. but logically, that seems to make sense. And on the reader, it's a little bit more difficult. You're definitely reading to acquire, both times. You're like acquiring a lock, inverted commas, then you're reading out stuff, and then you're reading it again. But again, it's a little bit more subtle than that, because the second thing is also a release in a way, because if you did get a good copy, you need to make sure that nothing of the copy leaks the other side of the acquire. It's easy with a picture, but it's subtle. It's subtle and difficult to get right, which is why it took 2 solid days and lots of testing. And that brings us to the next bit here. So it's very straightforward. It's somewhat straightforward to explain it without a picture and without a whiteboard around, in terms of this sort of hand waving things that compilers are allowed to reorder. It's much, much harder to prove that you got it right, because the output of the compiler may or may not encode this this like optimization barrier that you've put in. All you've said to the compiler is like, hey, by putting this acquire in here, I'm saying that no read that happens after this acquire can be reordered by the compiler north of this read, or whatever the acquire operation. But I can't. All I can get sort of circumstantial evidence by looking at the disassembly of it and kind of go, it doesn't seem to have done anything. I can't tell that in general it is not able to do that, because it depends which program I put it in. If I put it in a big program where lots of inlining happens and all that kind of stuff, I don't know if I have hinted to the compiler correctly that this is in fact the right thing to do. So that was a real challenge. And we've talked a little bit about testing these kinds of things before.
Yeah. Testing multi-threaded code in general is not easy.
No, exactly.
Yeah.
It's very difficult, and all you can do is kind of develop a certain amount of confidence that you haven't got something egregiously wrong.
Right. I mean, it's the same. I think it's the same thing with like looking at your compiler output, right? The best that you can do in that case is see that you were wrong. But if you fail to see that you were wrong, you don't know that you're right.
That's exactly it. Yeah.
So you tend to do, and I don't know if this is true of the sort of, decompiled analysis, but you can do a lot of things where you give yourselves lots of opportunities to see that you're wrong. Run the code on different architectures, run it with different sets of data, run it, multiple times over and over again.
Even,
different compilers, different compiler settings, I'm sure.
Yeah.
And you sort of like look for all of the possible opportunities to prove yourself wrong, and then you fail to prove yourself wrong, and then you just kind of give up and admit that you might be right.
That is exactly how. Yeah, that is exactly the sort of the approach that I've been taking, which is why it's taken quite so long, apart from just reasoning about it in the first place. And interesting, you mentioned about architectures there, because one of the gifts to programmers like myself of the Intel domination in server architecture, at least, is a very strong memory ordering. So one of the really cool things, I'm sure we've talked about it before, and certainly anyone who's seen any of the nonsense that I've put on the internet knows that I love the kind of amazing tricks that the CPU is pulling off under the hood. And one of its sort of real trump cards that has caused problems along the way is its ability to reorder and speculate instructions out of the sequence that you gave it them.
Yeah.
Very much like the compiler itself does, the CPU is able to find flows and sequences of instructions and reorder them to take better advantage of the fact, hey, I have a spare multiplier going now, but look, I can find a multiply that's like 300 instructions in the future, and I know what inputs are going to go into it, so I might as well start it now. All those kind of tricks. It's amazing. But when it comes to loads and stores to memory, it doesn't reorder those. Or if it does them in a way where it can track if it got it wrong and it can redo them later on, which is takes a bonkers amount of silicon to do. But it does mean that in general, if I go load, store on one thread, and on another thread I go load, I wouldn't. It's so difficult to explain this without a picture, but the sequence of operations will make sense. They're effectively, for most intents and purposes, there are exceptions to this, sort of effectively sequential, even in the presence of these kinds of atomic-like operations where you've got thread A doing one thing and thread B doing another thing. It's very hard to catch it out doing the wrong thing. So for the most part, even the naive code that's got it wrong, in air quotes, won't be wrong on an x86 because the compiler, short of it doing its own optimizations, the code that it generates will run in the boring, dull order that of loads and stores and increments and things that you gave it. That is not true in general of every other CPU on the planet. Because Intel love to be backwards compatible, and presumably the very first time they went multi-threaded, they went, oh, this seems like a useful property to have, unaware that it was going to hamstring them for like the next 25 years. But ARM CPUs, RISC-V CPUs, MIPS, and anything else, nothing else that I'm aware of has such a strong memory ordering. That is to say, if you do loads of a bunch of stores and loads on one CPU, they could be reordered with respect if you were able to observe them on another CPU.
Yeah.
Right. Okay. Obviously, they're not willy-nilly reordered to make your program wrong on a single-threaded case, right? That's not what I'm saying here. I'm saying that, like, hey, if you do load, store, and the CPU, it won't reorder those loads and stores from where you're sitting to give you the wrong answer. But you might see something weird and wacky on another CPU. I think there's the sort of cases if you do sort of like remember the value of A on one thread and then write B to be 1 on one, and then on the other one you go write A to be 1 and then remember the value of A. You can see a case where they both observed A and B to be 0 and then they both wrote 1 to the other, and there shouldn't be a way that they could do that, right? Again, paper. This is terrible podcast material. I'm sorry. So anyway, on those architectures, the atomic operations and the sort of like this acquire and release or acquire release type semantic thing that you give to it is not just a hint to the compiler to say, your compiler, you're not allowed to move these things around. It tells the compiler to put instructions or flags on the instructions that say, hey, CPU, you're not allowed to do reordering here. And so one of the other things that we were doing while we were like working on this was we were deliberately, although we don't run on any architecture other than x86, we were using the presence and the particular semantic interpretation of the presence of these serializing barriers or fences or loading instructions that have like particular properties about reordering that can happen. As a litmus test for not only do we observe the code to be correct on x86, but we observe the kinds of loads and stores to be the right kinds of loads and stores on ARM that says, hey, the compiler knows that it absolutely has to have let this increment happen before any of the following code completes.
Yes.
But again,
this is sort of like telling somebody something and then being like, okay, now explain it back to me.
I suppose it is.
Right. And to making sure that they understood what you said. It's like, are you going to put these things in there and see if the compiler reorders things in a way that doesn't make sense? And you're like, well, okay, maybe we're not on the same page here about what instructions need to be ordered.
Well, that's absolutely it. Now, obviously, there's still no guarantee that that's right. And there's still no guarantee that while the compiler has emitted those correct instructions, that it still wouldn't move things around above and below those instructions because it feels it has that degree of freedom. I can't introspect into the compiler and look at each instruction and say, given free reign, would you move this up further?
Right, yeah.
But that would be an interesting thing to do. So it has been an interesting few days. I mean, and the performance you get out of this is pretty astronomical. It's like on x86, it's, single clock cycles to read and write to something that is 16 bytes long. Now, for something that's 8 bytes long, you can just atomically write the whole thing and be done with it, and you don't need any kind of sequence lock. But if you've got 16, 24, 32, even up to like 48 bytes, single cache lines worth of work, this is still essentially free. Free. It's all relative in our world. So it's been a super fun thing. To the point where actually, someone was reviewing the code and saying, well, you say it's single-threaded writer. Can you detect the case where there are two writers and, throw an exception or blow up or, something like that? And it's like the answer would be yes, I can, but it would add something in the region of twice the overhead because just even the check and the read and the whatever and the out of band jump is actually noticeable at this level. It's pretty minimal. Don't get me wrong; it is pretty minimal. But and also, what you're going to do at this point? It's a bit late if you've got two writers. But it's nice to have in debug. So that's what we've done: is we put it in as a debug check, and then. But it's been a really fun and interesting journey, and in doing so, we've discovered a whole bunch of interesting other techniques that you can use to have something that have like different trade-offs between back pressure on the writer versus readers having free reign. The classic example of something that's a little bit more fair for the readers is a reader's writer lock. like an actual lock in this instance, where
Oh, okay.
the lock is an atomic value, and like the bottom 16 bits or the bottom 32 bits are how many readers are currently reading, and the top bit, or however many bits, is like, is there a writer?
Mm.
And then the readers, in order to acquire a lock, they have to do some work here. They acquire a lock and they basically try to atomically replace the value with one higher.
Mm-hmm.
And if it fails, they'll get, as part of the atomic switch operation that the CPUs can do, you get
Mm-hmm.
back what the actual number was, and you can see whether or not the writer was there. And if the writer was there, all bets are off. But if you were able to increment it, okay, then you've let the writer know that there's at least one reader. And so that's what all the readers, and you could have like 10 readers all reading from the same thing, and that's fine. They can all be reading from it. And then the writer has to do the other thing where it says, I need to be able to replace a 0, like literally there are no readers and no writers, with a top bit set value. And if I'm able to atomically do that operation, then I've locked out all of the readers, and I've got the lock, and I can spend my time writing to it.
Yeah. So just to clarify here,
Yeah,
when you
sure.
say there are, you've got these two halves of this, the upper bits are the number of writers and the lower bits are the number of readers.
Mm-hmm.
You're saying the number of things that are currently reading or currently writing?
Correct. Currently
Not
reading
like
and writing.
the logical number of readers and writers
This
in
is
the
a
system.
current thing which allows them. And
Yes.
so, yes. Yeah. And so at that point, what you're doing is you're actually preventing the data race. So that's an aspect we glossed over earlier, is that strictly by the book, taking that copy of the data while it was unprotected by any lock is
Mm-hmm.
not allowed by the C++ standard. It's an undefined behavior to read a
Mm-hmm.
value that's being updated. Even though we don't look at it, unless we know that we got a good copy, that's not okay by the C++ standard. And there's some papers out there that are trying to canonify it and come up with ways to make it like okay to do it. But ignoring that for now, right? There's coming back to this thing, in this particular instance, no, we are actually preventing any kind of data race, because the readers do take out the lock for the tiny amount of time that they're taking their copy or working on it, and then they reduce the lock. So it's it's not the number of readers, it's the number of readers that are currently reading and locked it. But they obviously, you can have as many readers as you like reading from it, and that's potentially useful again if it's some kind of shared piece of data. Like, this is the Linux kernel kind of example would be, hey, this is configuration information about which time zone everyone's in. There are many processes that are getting the time of day all the damn time. We never really, we want to allow them to make progress most of the time. They don't have to lock each other out. But there's only one writer, and it's the kernel. And every now and then he needs to be able to go in and say, hey, someone just did a syscuttle and changed the time zone, or whatever it is, whatever kind of shared information. Of course, the problem with that is that the readers, if there are enough of them, can easily starve out the writer. You can get a situation where the writer can never actually...
Oh, right. Yes.
And so then it gets more sophisticated, where you start using more bits to say, hey, there's a pending writer, and then the readers aren't allowed to get a lock if there is a pending writer, even though, and so on and so forth. So these things are complicated, but they're fun. They're fun and interesting. But at least that case doesn't suffer from the data race, the sort of strict data race by the book version there. But yeah, testing this has been essentially an exercise in all the things we talked about, looking at the disassembly, writing some simple-ish tests. And I think in one of our earlier episodes, you made a comment about, these kinds of tests have to be something like, you have to have seen it work once.
Oh, yeah. Right. Well, I had made the argument in an earlier episode that, write all the unit tests you want, and I do, but write all the unit tests you want. But if you've never actually seen this thing work in production, you have no reason to believe that it works, right? And the intention there is to, again, as we were just kind of talking about, you're passing on an opportunity to prove yourself wrong. And sort of moreover, like, it's one thing to say, like, okay, I wrote this, lock-free queue, and I pushed a bunch of data into it, and I pulled a bunch of data back out, and I've tried that a number of different ways with different data sets on different architectures and all these things, trying to prove that it doesn't work. But if you never even tried the base case of, like, did it ever work at all once?
Right. Then
you're just being silly.
That's true.
You're being silly on purpose. But that sort of rule of, like, have you seen it work once, I think is more applicable for things that are more mundane, that are like, pretty easy to get confidence that they work with just unit tests. The only question is, do you have enough unit tests, right? It's like, if you've never seen it work once, then you don't really, there's no reason to believe that you have enough unit tests essentially, right?
Yeah.
But this is a whole other thing, right? This is like, you can see it work 1,000 times and still not be confident that it's going to work the 1,000th and first,
That
right?
is, I think, the material difference.
Yeah. And you got to get much more creative about how to create that confidence, because unit tests alone and a little bit of exploratory testing, watching it work one time or 2 times or 5 times is not going to be enough.
Yeah, no, it's really. I mean, so when I put out that we had 4 different engineers review the,
Yeah.
and this definitely passes the test of like, as in general, I don't write comments in my code. I think I've said this before. I prefer to have explanatory names for things where it makes a lot of sense, and so rather than manifest. I mean, most people. A lot of people feel this way. You put sensibly named intermediate values or variable names, and then it's like it explains itself, because essentially the last line is a piece of English prose, right?
Yeah.
It's great. Return interest rate times whatever. There you go. They don't have to explain it. But this code has somewhere in the region of 50 lines of non-comment, and it's a 200 or 300 lines of header, right?
Yeah.
It's like the ratio is obscenely the other way, because there's a huge setup explaining how the general thing works. Then above every single line, there's my reasoning why it's okay to have it in this particular sequence and order, why there are these flags set, which other lines of the code it kind of interlocks with, in terms of if the other thread was doing this thing on this other thread. But yeah, so anyway, it went to review. 4 engineers looked at it, and all of them so far have said, yes, looks good to me. But one of them brought up a really interesting point, which was like, there are formal verification systems that for multi-threaded programming that you can use, where you describe in a sort of DSL the operations that you're doing, and then a sort of theorem prover runs and shows that there isn't a window of opportunity where things are wrong. And so, for example, if you're designing, I don't know, the Paxos protocol or the Raft protocol or whatever, then this is the kind of thing. If you can explain your protocol algorithm to this system, it can say, yes, I can prove that there exists no opportunity for this to give you the wrong answer.
Yeah.
And that was a really interesting case, interesting observation. But unfortunately, they don't run on C++. They run on the description of the system.
Right.
And that's where I fell over, in terms of like, I don't know that this is going to help me here, because I quote, know that sequence locks work in theory, because they're in the Linux kernel, and I've got 5 different there are 5 different open source things that have very wildly different atomic operations in them. And so I was like, no, let me try and reason this from first principles so that I can defend why we're doing it this way. But I would have no confidence that any explanation of what I had done to a theorem prover was a good representation of what the C++ semantics were.
Right. Yeah. It's the difference between the algorithm and the implementation. You
Exactly
can prove
right.
that the algorithm is correct using the theorem prover. Prove the implementation is correct is much more work.
Yeah.
And the other thing is, we mentioned this at the start of the podcast. We were like, well, assume no latency constraints, and this problem gets a lot simpler. When you add in the latency constraints, you were talking about the sort of ratio of code to comments.
Yeah.
It's like you have to, it's like the square of the comments now, because you have the dimension of thread safety and the dimension of latency, and you're doing both of those things at the same time in the same code, right? And that's going to make it much, much, much harder.
Yeah.
Because, the cycle time, at least, it's like, okay, we figured out some way to improve the performance by another 30%. And it's like, okay, and how do you know that this hasn't completely broken your threading model? Well, we don't. So we get to do all of that testing all over again.
Yeah, that's the thing. I think, like, one loses the warm, fuzzy feeling that, like, you can touch this code in any way and not go through some, like, non-automated handoff. Obviously I will check in the test and the smoke test that runs for 5 seconds and make sure that, like, nothing overtly stupid happens will remain, and I'll leave that in. But I can't, or I don't want to I can't think about having, like, oh yeah, this is it, we run it through Compiler Explorer. Effectively, I've actually been using the site to do something for a change, through here's 6 different architectures, and then it should exist that there should be no LDR of this variable before the LDAR, that's the serializing load, blah blah, that kind of stuff. That one could go as far as that, but I don't know that wouldn't be so brittle that it would. Yeah, I don't know, actually.
Yeah.
Maybe that is the way to do it.
Well, the golden rule of all of these things, and especially if you have something that is this, like, thread safety and latency sensitive, is design it in a way where you won't have to change it, right? Like you're going to do all this upfront cost and all this really hard work to get this code just exactly the way that you want. Make sure that you encapsulate it really well so that the chances of you having to change it are as minimized as you can make it, so that you can just kind of leave it there.
Yep.
And then, go into Git 5 years later and be like, yep, this code hasn't changed in 5 years. It's been working for the 5 years. That's as confident that I'm ever going to get in any piece of code like this that it actually works. So please don't change it. Right.
That is a very, very good observation. In fact, one of the review comments was I had an interface that was slightly more open-ended, and you could do some cool things with it, because I could. I gave up this. Hey, rather than just replace the value, I was like, well, the reader can. The writing thread can at any time read it. It knows no one else is changing it because it is the only writer. So like you could actually update it anytime you like by looking at the current value and like maybe incrementing it rather than replacing it. And then one of the reviewers was like, yeah, I don't think I'm a user of this. I'll be a user of this and I will never want to do that. Yeah, and so I took out the interface. It's just like, okay, you've got get and you've got set.
Right.
And maybe, just maybe, I will have get, but I promise Scout's honor that I am the writing thread, and as such, I'm allowed to get it without any kind of lock promise function that will allow the other access type. But yeah, it's been an interesting few days, and I figured it would be a fun thing to talk about. And I said to you, this is probably going to be a short one. I've just looked at the timer, and if we haven't lost absolutely everybody with my attempt to try and describe multi-threading memory ordering problems, then I don't know what will get rid of listeners.
We're trying our best here.
Yeah, no, this has been fun. Thank you for letting me talk about my
oh no,
project.
This is super cool. I love this stuff. I'm a big fan.
Well, maybe next time we'll talk about something a little bit more human.
I don't know, we can talk about more of this. I'm down with that.
That's cool. Actually, yeah, we have done a lot of humaning recently.
Yeah, so right.
We're probably due a bit more tech content. Although, to the extent that folks have contacted us, and we encourage you, you can contact us at the Mastodon hackyderm.io or whatever it is, or email. You can find our emails. We always love to hear from our listener. Folks were very positive about some of our more human focused and less tech focused stuff, but we can get back to tech as well. That's cool.
I take the philosophy that the human elements of software are inseparable from the technological elements.
Yeah,
they are sort of one and the same thing. It's hard to see that, but it really is true. And if you want a great example of this, take a code base that was written by other human beings and give it to a different set of human beings and then watch them.
Oh my gosh.
And if that doesn't convince you that technology and people are intimately intertwined, I don't think anything will.
We really do need to stop, but Kate Gregory has an amazing keynote speech where she talks about the empathetic programmer or something like this, and it's like all about that. It's like, you should have empathy because who's going to be reading this code. It's going to be your friends, your colleagues, and also probably yourself. And obviously,
yes, future you who has slept since then and has no memory of what any of these things do.
Exactly. All right, we should stop now, but this has been fun. Thank you very much, and I guess we'll see you next time.
Yep, till next time.
You've been listening to Two's Complement, a programming podcast by Ben Rady and Matt Godbolt. Find the show transcript and notes at www.twoscomplement.org. Contact us on Mastodon. We are at twoscomplement@hackyderm.io. Our theme music is by Inverse Phase. Find out more at inversephase.com.